So in this lesson, we're going to talk about something called slope fields. It's going to feel like a very weird lesson at first. It's very closely related to differential equations, and it's something that's very, very big on the AP test, okay? So let me kind of run you through what we've got in this first paragraph. So even if you can't solve a differential equation, so typically the reason that you'd want to use slope fields is if you can't separate, integrate, and solve the differential equation. For all the ones we've seen, we can. And actually, for all the ones that we'll do slope fields with, you still can. It's just a good idea to know how the slope fields work. So the differential equation, remember tangent lines have the same slope as the differential equation would be. So it's like we have this field of like teeny little tangent lines. And that's what we end up looking at. All right, so if you're looking right at the point of tangency, if you zoomed right in, the little tangent line would look just like the graph. Okay, so what you do for slope fields is you draw all these teeny little tangent lines. So at like the point 1, 1, you draw a teeny little tangent line based on the differential equation. At 0, 0, you write a teeny little tangent line. All right, because you know what the slope should be there based on the differential equation. All right, so I'm going to give you a quick definition of what we're looking at here. This is a collection of line segments with slopes equal to the value of the differential equation. Okay, so like I said, so the little, like teeny little line segments, the definition sounds really weird until you actually look at what these things look like. But the line segments have the slope that you'd get by plugging the point into the differential equation. Because you know differential equations, they usually have an x, maybe a y. So for the point 0, 0, for instance, you'd plug 0, 0 into the differential equation. Say you get 1, you'd write a teeny little line segment with a slope of 1. So let's look at an actual example on the next page. We're just going to do a really easy example. And it's something that we could actually solve for. So very basic example. Let's say that the derivative is 2x. And we know if the derivative is 2x, then the equation itself is x squared. All right, so this is our little equation. So every single one of these points right here, we're going to make the teeniest little line segment that has this derivative at that point. So like, let's start with the point 0, 0, for instance. I don't need to plug anything for y, but if I plug in 0 for x, that means I would have a slope of 0. All right, so you draw this little line segment with a slope of 0, which is just a horizontal line. So if I'm looking anywhere along this axis, the x value is 0. And this is only affected by the x value. Okay, so the x value is 0, so I've got a slope of 0, slope of 0. Okay, so any one of these points, you know, the point 0, 1, 0, 2, 0, 3, 0, negative 1, 0, negative 2, 0, negative 3. If I plug in the 0 for x, they all have slopes of 0. The reason that it's the same up and down is because there's no y in this differential equation. So now if we move over to the next strip, all of these have an x value of 1. So if I plugged 1 in here, I'd have 2 times 1, which is 2. So you just do your best at making a slope of 2. I always kind of point it at this one, because you could go like up 2 over 1. So if you kind of point it like it's going to go toward this line, it'll look like that. And then do the same thing, like this one, point it at this point, look like that. It doesn't have to be flawless, you know, just as long as it's not like negative. This one, you'd point at this line, this one. All right, so those should all look something like that. So now let's move over here. These ones are negative 1. If I plug x equals negative 1 into this equation, I get negative 2. So at these points, the slope would be negative 2. So same thing here. This one, you can point down at this. So you point down there. This one would point down here, 2 units down. Okay, so those are all slopes of negative 2, and then we can move out. So here when x is 2, my slope would be 4. Okay, so all you need to do is just make it steeper. So like this one, for instance, you'd actually point 1, 2, 3. You'd actually point down here, which makes it just a little steeper. Basically, as long as you make it a little steeper than the last one, you're good. These don't need to be like the most accurate thing in the world. And then these would be 6. So 6 is a very, very steep line. I mean, these are practically going to be vertical. All right, then we do the same thing over here. This, when x is 2, my slope would be -4. Sorry, -2. My slope would be -4. So make them a little steeper than the last ones. And then here, when I plug in -3, my slope would be -6. So these ones are very, very steep little lines. Okay, it's like we're pointing at an ordered pair 6 units down. Okay, so that's my slope fields. That's a perfect example of what a slope field looks like. So we've drawn little line segments with the correct slope at each point. So now let's look at this. This we should know. If the derivative is 2x, what that means is that my original equation is x squared. And then, of course, I have a plus c. That's why we call it the general solution. So the general solution is this right here. And what this is a family of parabolas centered on the x-axis. And the reason that these values are so cool is because you can look at a particular solution. So I'll show you. It outlines a whole family of solutions. So if you look closely, kind of use your imagination, you can see these parabolas centered at the origin, parabola centered at -1, -2. That's exactly what the slopes are doing, is they're kind of forming out a little parabola. Now obviously if I had more points on here, it would look more like a parabola. Typically slope fields are not every unit. They'll be every like quarter unit or something like that. But if we want a particular solution, this is something you'll have to do on the AP test. So you've got this. We want to go through the point 1, -1. So here's the point 1, -1. So basically you just kind of follow this. This bounces you down. It's going to go down here, come up on this point, get steeper. It's almost like a pinball machine. Like they're bouncing you off. And so a particular solution would look something like that. It's a parabola. It's centered on, oops, not the x-axis, the y-axis. Wake up. Okay, so it's centered right on this y-axis, and it's going to look something like that. It goes through that point. You could do any particular solution. They could give you any point, and you'd be able to sketch out an approximate. It's never going to be flawless, believe me. But you could sketch out what an approximate parabola would look like that goes through that points. Okay. So last thing we're going to do, and this is going to be pretty quick, we've got a family of, or a whole bunch of slope fields and then a whole bunch of equations. And one of the most important applications I can teach you is how to match a differential equation with a slope field. Okay? They're most useful when you can't solve the differential equation. Because if you can solve the differential equation, you know what the original function looks like. Sometimes separation of variables doesn't work. Sometimes you can't get all the y stuff on one side and all the x stuff on one side. All right, but we still want to see what the graph of the solution would look like. So let's flip on to the next page. Okay, so 6 examples of slope fields. We want to match them with the correct differential equation. Okay, so lots of different clues that I can give you guys. So notice here, like this one only has to do with x. This one only has to do with y, only with x. Both only with x, only with y. Okay, so that's actually going to make a huge difference, because if you look back at this example, this differential equation only had to do with x, and so as you moved up and down, the slopes didn't change. This is like a perfect strip of the same slope, same slope, same slope. So we can narrow these down. So like this one, for instance, this, as you move up and down, it's got the exact same slope. So this one only has to do with x. We know that for sure. This one does the same thing, actually. As I move up and down, all the slopes are the same, which means they're unaffected by y. So this one only has to do with x. Now let's look at this one. This one, as I move up and down, they change, but as I move left and right, they don't change. So that means this y value all has the same slope. This y value all has the same slope, which means they're unaffected by x. So these are only to do with y. So we can kind of narrow down, and these are just good slope field techniques that I'm giving you. If you look at this one, as I move left and right, the slopes are the same. So moving left and right, there's no difference, which means x does not affect it at all, which means it's only affected by y. And if we look at E, okay, so take a look at E. This one, as I move up and down, my slopes don't change. So it's unaffected by y, which means it's only affected by x. Now finally with part F, as you move up and down they change, as you move left and right they change, which means this is affected by x and y. Okay, so using that as kind of a process of elimination, there's only one differential equation that has to do with both x and y, and that's number 4. Okay, so you know this one must be number 4. Okay, and I can kind of explain why. X plus y, that's where you're getting your differential equation from. Notice as you move down this diagonal line right here, this diagonal line, your slopes get pretty close to 0. And that's because that's the line y equals negative x. So if y was negative x, this would be 0. So you can look for things like that. Okay, so 4 matches with F. Now let's look at the y ones next, because there's only 2 options. Okay, one of the next most important things you can look for is where the slope is 0. Okay, so here, your slope is 0, maybe somewhere around 1. Looks like right around 1 your slope would be 0. So if you look at this equation compared to this equation, here if you plug in 1, you get slopes of 0. And so that means that this matches with C. Okay, so that one's 2, this is C. So now this must be the other one, but let's double check. This equation says if I plugged in 0 or if I plugged in 3, I would get slopes of 0. So let's compare right here. Okay, so if I'm plugging in slopes of 0, we can't really tell, but it looks feasible. Looks like that seems about right. And then I don't quite make it up to 3, but it looks like they're headed towards 0. And then most importantly, as I go down here, my slopes are getting very, very, very steep. So as I plug in low numbers, this is a low negative number times an even lower negative, times a big positive number. And so those are going to be steep slopes. So 6 is going to match with D. Okay, so now I'm just down to just the ones that look like X. Okay, so there's a couple things you could do here. The slopes of 0 are a big clue. So here, the slopes would be 0 when x is 0. So that's not this one, because the slopes aren't 0 there. When x is 0, so we're going up and down. It's not this one. Could be this one, because the slopes are all 0 right there. And it also could be this one. All right, the next thing you want to look at is one of the slopes positive and one of the slopes negative. Okay, so here, if I plug in positive values of x, I get positive slopes. Here, if I plug in negative values of x, I get negative slopes. With this equation, my slope should always come out positive, because if you square something, it comes out positive no matter what. So it must be this one. This one, if I plug in negative numbers, I get something negative. If I plug in positive numbers, I get something positive. Plus, this looks just like the one we graphed, which was 2x on the front page. So this is number 5. There's part B, which must mean that the 3x squared goes with this one down here. Notice 3x squared will always spit out positive numbers. These slopes are always positive. All right, so this must be number 1. This is E. And that leaves A as cosine, which should make perfect sense because the antiderivative of cosine is sine, and this looks just like a sine function if you kind of follow your slopes here. All right, these slopes of 0 come right around here, and cosine is 0 at pi over 2, negative pi over 2, so that would be right around here, right around here. So this is our third option, and this is A. Okay, so I know this stuff feels very weird at first, but we're going to get a lot of good practice with this tomorrow, and I'm going to give you guys kind of a concise list of tips that you can use to match up slope fields. All right?